name's Kyle. This is lab number 4. So I'll start off by introducing the lab, going through the procedure, computational model, data analysis, errors, and then what it means. Start off by saying this lab focused on an object and on a spring and pendulous system where we had to track the movement of a mass attached to a spring in the y and x direction as it drops into oscillatory motion. And then in addition, we are comparing the observed data to a computational model which we made in GlowScript. And the main result from our lab was a pretty close computational model, closely matching the experimental data with some slight differences in both the x and y direction. In performing this experiment, we're able to use the data to verify the accuracy of the law of conservation of energy and see how different types of energy can interact within a system with the spring and gravity. Law of conservation of energy states that the total energy of an isolated system remains constant. As a result, we're able to see how these different energies are able to interact with each other. So here's some of the equations. We start off with our velocity and position update formulas, which we use every time. Then you have the kinetic, spring potential, and gravitational potential energies, and then the energy conservation formula. So our procedure, we started off by going through the video on Canvas, putting it into Tracker, figuring out where the points were by using the mass tracking. And then once we had a data set, we put it into Excel. We exported it as a CSV file, and then using the starter code in GlowScript, we accessed the code, set the initial conditions, change around some variables by using initial conditions as well as other variables, ran the code, put it in our CSV file, and then we got a graph which we observed and analyzed. So some of the assumptions we made while running this experiment are that the only forces acting upon the mass were the spring and gravity, as well as assuming the tracker placements on the mass were consistent throughout the entire motion. So some of the initial conditions are the mass of the object, initial position, initial velocity, which you can see here we got from our tracker data, the starting time, delta t, which was already in there, g, which is just our gravitational constant, spring constant, which we solved for, and then L naught, which we observed in the video. Some of the formulas that we use and their computational parts in the code. So we have the velocity update formula, where obviously it's just the initial velocity of the ball plus you get the acceleration divided by m, you get the acceleration by dividing net force by m and getting multiplying that by delta t. Then you have the position update formula where you take the initial position of the ball and add it to the displacement. And then for the energy conservation formula, we're able to basically see that the change in energy is going to be 0 for the system, and the net force of the system is going to be the force of the spring plus the force of gravity. Here are some of the energy formulas. We have kinetic energy, 1/2 mv squared. Gravitational potential energy, U equals mgh, where h would be the position of the ball, and spring potential energy, which would be 1/2 kx squared, where x is the compression. So L is the length of the string in terms of where it is at the moment. So we call that L, right? And it's the position of the ball minus the position of the spring. L hat would be L divided by the magnitude of L. And then S is the same thing as in our 1/2 equals kx squared, it would be x. So it's the compression of the spring. Here's our code for part 1. You can see in the GlowScript results, we have closely matching data with part 1. The first graph shows all the different energies, and then at the end of the day, our net energy. And then the right top shows our x position over time, and bottom one is y position over time. Some potential errors or improvements could be in putting our points on tracker. Potential issues with accidentally giving the mass an initial velocity, and then maybe potential rounding errors. So what does it mean? So is the energy principle satisfied? Yes. So if we look at our graph, you can see that our delta E remains at 0 throughout the entirety of the motion, which means that it's constant. You can see fluctuations in like all the other ones, like kinetic, gravitational potential, and spring potential. But at the end of the day, our net delta E is always 0. And then using the tracker and data, what do we get for our oscillation periods? Here I just took 2 points that were in the same part of the motion, and I got the time for each, subtracted them. For X, you get 1.629. For Y, you get 1.529. They're pretty close. And yeah, thank you for watching.